All right, we'll get started. Okay, before we jump in, are there any questions about anything? No? Okay.
Well, for the assignment,
Yeah.
so I wrote down the 7 core tasks.
Yeah.
Then you want to be able to write 1 page on each of the tasks and how.
You'll do the cognitive walkthrough of each task. Yeah.
Okay.
Yeah, and it will be about a page, like 3 pages for the 3 tasks.
Okay.
So about a page per task, but if one's longer, the other one can be shorter, that type of thing.
Okay.
Yeah. Any other questions about the assignment? Okay, good. All right, so we'll keep going with the SSL attacks. So we're going to do 2 weeks, so we'll talk about it this week. And then whatever we don't cover this week, we'll cover next week. Next week won't be like a ton of content. Like it's about 2.5 lectures instead of 3. And I don't want to move on to the next topic until we're done this one. So what I think we'll do is, because it's the Friday before reading week, whatever we don't cover by the end of today, I'll put a lecture online, and then you can just watch that. So we won't have a class next Friday before reading week. But there will be a little bit of material, like maybe 45 minutes or something like that. And so then there'll just be a recording. Whoops. Yeah, so when you go to Moodle, it will. I'll just slice it into the playlist of the videos anyways. And that will be next week, yeah. Is that clear? So no class next week, but there will be a lecture, it just will be online instead of in class. And it will be shorter than normal. And then the following week is reading week, yeah. So you'll get an extra day for your reading week. All right, I'll put it on Moodle too, or maybe send an email reminder or something. Okay. Okay, so you'll recall we're talking about attack trees, and I don't know why the lights keep going on and off.
Maybe it's on sensor bandwidth.
Yeah, I don't know. Okay, we'll see what that is. All right, so we're trying to break into the tunnel. We're already in a man-in-the-middle position. And we have 3 general strategies. So the first is just see what we can see from outside the tunnel. The second is to actually try to break into the tunnel. And then the third is to get the tunnel pointed at us. So this class we'll talk a bit about the second tunnel, and then the second class of attacks, and then we'll talk about the third after. Okay, so last time I think we ended on side channel analysis. So I'll show you another way that you might try and get a key out. So this is a historical incident that happened. It was called Heartbleed. It was a vulnerability. I'll explain what it was. It was pretty famous. So like, for example, if you just turned on the news, for that day or a couple days, you would hear about Heartbleed in the news. Okay, so what this was is it was a vulnerability. It was on servers, not on clients. It affected servers that were running something called OpenSSL. So OpenSSL is a library that provides TLS support for doing HTTPS. Any site that runs HTTPS will have an SSL library. It won't necessarily be OpenSSL, but it will be something. The most common server operating system to run is called Apache. So it's open source, kind of a Linux variant. Windows is probably the second most popular. And so this affected, OpenSSL is the default SSL library for Apache. Windows has their own stack. So if you're on Windows, you probably aren't using OpenSSL, although you could potentially. And OpenSSL had this protocol called Heartbeat. And so you would need all three of those things enabled. So you'd have to be running the Heartbeat protocol in OpenSSL, which you'd probably be running on Apache. Okay? Lots and lots of servers had this stack. So something around half of the servers on the internet, it's estimated, were vulnerable thus to this attack. Okay, so there's this Heartbeat thing. I'm just trying to get my mouse. I don't know why it doesn't want to show. Okay, there's a Heartbeat protocol. It's built into SSL. SSL is like a very old library. I think, if I recall correctly, the person who coded it up in the first place, like did the first version of it, just wanted to learn C, had never learned C before, and he's like, okay, I want to learn C, so I'm just going to code up a crypto library. But then because it was open source, it became a predominant library. And so there were some like weird things that it would do. And so this is one of them. It was a feature that basically no one used. I think everyone sort of forgot that it was supported, but it was there and it was live in the code. And so the Heartbeat protocol, what you could do is you could basically just send some bytes to a server that's running OpenSSL, and it would repeat the bytes back to you. Okay, so it was kind of like a liveness check or like a configuration thing, so you could just check and make sure that the library is working and you can see through, the ports aren't being blocked, the traffic's not being blocked, that kind of thing. Now, it had this extra feature, which is that you can send it a string of bytes, and then when it echoes back the bytes that you sent, you could ask for less bytes than what you sent. So you could say, I'm going to send you a bunch of bytes, you just tell me the first 5, and then I'll believe that you're responding, okay? Now, this doesn't make a lot of sense because you could have just sent 5 bytes in the first place. Like, why send more bytes just to have it echo back a few? But anyways, that's basically how it worked, okay? Anything about this seem kind of suspicious?
Yes.
And what?
For example, so let's say an adversary that doesn't like maybe wants to access a previous information or something, could like echo to the server, and the server not verifying who that person is going to respond with sensitive information.
Okay, so that's exactly what Heartbeat will do. But what would you, if you looked at this protocol, where would you try to attack? How would you try to get sensitive information?
I can just stay in the middle.
Okay, so this isn't a middle protocol. Yeah, okay. That's a little different.
Then I'll be the one to send the message. I'll impersonate like the client, and I'll send the message or a big request to the server, knowing that it's going to respond to me.
Okay, so you could try to mix code into the message itself and have it execute.
Yes, there's also that injection. But
Yeah. So you could do some sort of code injection. This is not that. So there's two, like, if you go way back to the 1980s, there's kind of like 2 classic attacks. One of them is code injection. This could have been vulnerable to that. That could have been the attack. But it's not, it doesn't happen to be the attack. There's another like really kind of classic attack.
You can say echo -1.
Okay, so what if we play with that integer 5? Yeah? So what restriction should be on that integer?
Should be between 0 and the length.
Okay, so it should be no less than 0. We agree? Yeah? And it should be no bigger than the length of the string that you sent. Yeah? If you were permitted to do that, to submit a different number that wasn't checked, or if those bounds weren't checked, then there might be a problem. Okay? Now, this is written in C. I don't know how much you know about C, but let's say I have a string of bytes and it's written into memory. How do I know that it's a string as opposed to anything else or where the string starts, where it ends, how do I compute the length of it.
Characters before and after that will tell basically whatever's reading it, like start here and there.
Okay, so the code is going to just say start reading here. But the difference with C from, say, Java or a lot of programming is there's no end here. So what C will do is you'll just point it at the first byte of the string. And it doesn't know it's a string or anything. You just, as the programmer, are telling it it's a string. So it believes it. And it will just keep going until it hits a null character. Once it hits a null character, then it will stop. Yeah? But otherwise, it will just keep going. Yeah.
Are they like making an echo further than what it?
Exactly. So we could, if a -1's a great idea, I don't know what that semantically means, like to send -1 bits, but we can try and go in the other direction. So let's say we send like an 8 bytes and say, give me 1,000 bytes back.
It just reads other stuff that isn't in the actual message.
Exactly. So then what the C program is going to do is it's going to start at that byte. It's going to read 1,000 bytes, and it's going to send all that back. It doesn't know that it hit the end of the string because all the memory gets mixed together. Okay? So there should be bound checks on that, right? So the code has a bug. There's a flaw in the code, which is it's not checking whether that 1,000 is longer or shorter than the string that's being sent. So buffer overflow is something that you've probably heard of. This isn't, we actually call it buffer overread. It's slightly different, but it's the same concept of you should only be reading within a certain range, and instead you're reading in a bigger range. Buffer overflow is where you write in a bigger range. This is where you're reading, but it's the same concept. Okay. So what the protocol would do is it would let you basically suck out 64 kilobytes. That was kind of the max number that you could put there before C would say that integer is too big. So you could grab 64 bytes of whatever happened to be sitting in RAM up against the string that you sent to it. Okay. What would you expect would be sitting in RAM on a server, like a web server that's just running?
Password
Okay, why a password? It's the right answer, but why?
is one of the things that you would store on a server.
Okay, so this is RAM. So remember, RAM is the
RAM of a server.
yeah. So it's the operational memory. It's not the hard drive of it. Yeah, but passwords. Every time you submit a password, it has to take it, hash it a bunch of times, and then compare it. So it has to sit in RAM for that period. So what you'll get is you'll get the passwords of recent users who have sent their password to the server. Yeah. What other kinds of things could be saying there?
The HTTPS.
Okay, so something to do with the HTTPS, maybe the session keys. So that's going to be a problem that we'll think about. Yeah. Cookies, so any value like a session ID, that kind of thing. That's the kind of thing that could be sitting there. Could just be confidential information, like people are submitting stuff, to the server, and it's keeping a record of it. It goes through RAM, and so it's just sitting there. All right, so you could get usernames, passwords, cookies, data from other users, basically any kind of recent data that would go through the server. And then we can turn to TLS, okay? So every time you make a connection, there's what's called a key, a cryptographic key that protects it. It's called a session key. And let's say 10,000 people connect to Google at this particular time. There will be 10,000 keys. So Google will have a different key with each person, okay? So session key is unique to that connection itself. But in order to make that session key, there's this sort of cryptographic song and dance that happens, and it uses a long-term key that Google has. So Google has a key. It's packaged in this thing called certificate. Well, you'll know what that is soon enough. And it's something that that they have for like 2 years. Like Google's key is Google's key for 2 years or something. Okay, everyone knows what that key is. And so it's used for issuing digital signatures, typically. Okay, and to go along with it, there's a private key. And so the private key does the signing, and then you use the public key to verify that the signature is correct. So that private key will be sitting in RAM because every time it does one of these connections, it has to sign something in order to make the connection. Okay, so it's going to be sitting there. Now, the thesis, though, was that it would be very hard to extract it from Heartbeat because as soon as you open up SSL, it's the very first thing that gets loaded into memory. And because it's kind of like a stack, what will happen is, other stuff will get written to memory. And so by the time you are able to do Heartbleed, there'll be so much other stuff that's been in RAM already that you're never going to be able to dig deep enough. If you can only go 64 KB deep, you're not going to drill down far enough to get that key out. Okay, so that was the thesis. One major, I think it was a CDN, I forget which one. It basically said that that we're not scared about these keys leaking due to Heartbeat. We are scared about a lot of stuff like passwords and cookies and private data, but the long-term key should be safe. Even in theory, you could extract it, but in practice you can't. And then some hackers took it as a challenge to try and see whether they could extract it. And so what they did successfully was they would first send a vulnerability that would crash the server. It would force the server to reboot. And then as soon as it came online, they would hit it right away with Heartbeat or Heartbleed. And then they were able to get the key out. So they were able to demonstrate that if there was another vulnerability where you could crash the server and make it reboot, then everything would be fresh and no one had connected to it yet. Then it was possible to extract the key. So like I mentioned, it was you could go to CBC and there would be articles about SSL, like on CBC or whatever. There was one student, he was a high school student, I think, and he was just playing around with the attack, and he was just trying to, it was in Metasploit or something like that, and so he was just, trying it out. So he went to Canada Revenue Agency and tried it, and it worked. Then he did nothing, went away. But the problem was that all these companies, they have logs, server logs. So it took a while, but eventually they were like, okay, we realized that we were vulnerable to this bug. Let's go back to the server logs and see if anyone exploited it. And so they were able to do that. And so they found his IP address and then they tracked him down. And it turned out it was just a high school kid. He wasn't doing anything malicious as far as we know. He was just experimenting, right, with it. But he was charged, and he didn't. I think his sentence was very light. I don't think he didn't get jail time or anything like that. I forget, maybe community service or something like that. But he was actually charged in the end. So let that be a lesson to you as well. If there's a new attack and it drops, and you're just curious to try it out and see whether it works on real life servers, you can't do that. Okay? Yeah, you can test it in a sandbox. That's fine, but you can't just go out and test it in the wild. Okay, questions about Heartbeat? Now, the other thing
I'm just curious, what was the order? So did they realize it was vulnerable before anyone took advantage of it?
Yeah,
and
yeah.
Then they sort of said, oh, but we're not worried, and then people started trying.
Okay, so yeah, I didn't explain it very well. What happened is researchers dropped the attack. So it dropped one day, and they're just like, hey, there's this vulnerability in OpenSSL. And I can't remember if they notified, so the ethical thing usually is to disclose it first. So they may or may not have done that. OpenSSL may or may not have updated it, but lots of servers won't update right away, kind of thing, yeah? So when this bug dropped and everyone realized it, there were still lots of servers that were vulnerable to it. So this kid read about it in the news, or maybe in the tech news at that point. So he knew about the vulnerability, and then he tried it before Canada Revenue Agency was able to update their servers. Yeah. Sorry, Yeah. So if he hadn't, no. So he did it from his home in London, Ontario. So that's why. Yeah. But he wasn't thinking. He just wasn't thinking about the fact that it was a crime or that people. Yeah.
Yeah, Tor wouldn't be really useful for it.
Well, Tor would protect his IP address. So then they would see that somebody breached it, but they wouldn't know who. They wouldn't be able to trace it back to.
But if you use Metasploit, that's an application it would be running on the internet, right?
Sorry, yeah. So Heartbleed may have made it into Metasploit, or he might have just ran it by himself.
Oh.
I'm not sure which. Yeah. Okay, the other thing about Heartbleed is I'll say, so this would let you steal the session keys. It would let you break into the tunnel, or you could steal the long-term secret, then you could enter the tunnel as well. So that's why it's coming up in the context of this attack tree. But the fact that it happens to be on OpenSSL is sort of a coincidence, okay? The main point is there was this vulnerability where I could dump the contents of RAM of a server. That's what's relevant to the attack tree on HTTPS. The fact that it was actually an SSL library is interesting too. It overlaps, but it doesn't really matter. Like if this story was about another library that had nothing to do with SSL, it would still be the same attack, which is that you can get stuff that was on the server. Okay, other questions about this? Okay, another kind of attack you can do is called a downgrade attack. So with HTTPS, there's lots and lots of different options that you have. So there's different versions of it, and all the cryptography can be negotiated. So you can, basically this client will start and they'll say, here's all the crypto algorithms that I know about based on what my browser is or my operating system is. And the server will say, okay, here's the ones I know about, or they'll compare the two and then they'll pick the one and say, okay, we're using this one. But if there's an adversary in the middle, what the adversary can do is the client can say, I want to use really strong encryption. And the person in the middle can say, I want to use really weak encryption. I'm old. I don't have the latest libraries. Give me the old one. And then the server will just think that that's what the client's asking for. So the server will choose an old one. Then the client will receive it from the server. And then the client's thinking, oh, the server's old, right? So neither of them know each other, right? They're both thinking the other one is old. And then you could potentially end up with either a weak cipher suite, or it could also just be an old version of SSL. And there's maybe vulnerabilities. There are for sure vulnerabilities in older versions of things. So the reason this is possible is because of backwards compatibility. You never know when you're going to hit an old server, so browsers have old stuff. And servers never know when someone's going to come to them with some unpatched version of Windows XP. And if they want their website to work for that person, they're going to have a bunch of old stuff lying around as well.
Is there a way to like stop that from happening?
Yeah.
Like backward compatibility and all that?
Yeah, so this is how SSL protects against it. So what happens is you have this conversation about what you want to support, okay? And there may be a person in the middle, and they may get you downgraded at least temporarily, okay? So both parties are thinking the other one is old. But then this is the brilliant bit. At the very end, the last thing you do is once you have your keys and you've established them, you now have a secure tunnel, and you have message integrity, not just message confidentiality. So messages say secret, but now you also have whatever message I send, the other person's guaranteed to get. Yeah. And when you downgrade, you actually break the weakness of the confidentiality, but there's no way to really downgrade and break the integrity. Yeah. So the very last thing that you do before you accept the connection is you say, here's a record of everything I heard you say. And then the server will do the same thing. It will say, here's a record of everything I heard you say. And then you'll look at it and you'll look at what you actually negotiated. And if they're saying, I heard you say you only support some weak encryption, and you're like, no, I sent a message that said I support strong, then you will reject the connection. Yeah. So SSL was saved because it did this check at the very end. And because you couldn't, even though you could weaken the confidentiality of the channel, so you could weaken the encryption so that you could read it, you couldn't weaken the integrity of the channel. So they got lucky. But sometimes the way it was implemented had these vulnerabilities. So even though the protocol was technically sound, there were like software mistakes and software errors that would let you do this. And so there's a bunch of attacks. I'm not going to go through the details of them. But. Okay, and then I just pulled one sort of random attack out just to show you how sophisticated they get. And this one's good because you don't really have to understand anything about crypto to understand it. So it's called crime. Okay, so crime's kind of an elaborate attack. but it uses a scenario that's actually fairly typical of these sort of attacks on SSL. So we have an adversary. The adversary's in the middle. They can listen to all the traffic. So that's where we're starting with the attack tree anyways. What I'm going to do for this attack is I'm going to give the adversary an extra power. Okay. What the adversary is going to be able to do is get you onto their website, or at the very least, get you onto a website where they have some JavaScript running. And then in both cases, what they can do is they can open a connection to any website on the internet. So once you download either the adversary's website or some JavaScript from them, JavaScript has the power to say, go to this server and grab this image, go to this server and grab this image. They can send you wherever they want. They can send you 1,000 times to the same server. And what will happen is if you're logged into a website, let's say you're logged into Google, and the JavaScript is sending the Alice here. So Alice doesn't know what's happening. It's just happening under she just goes to a website. That's all she knows. Okay. But the browser, it starts running the JavaScript, and the JavaScript tells the browser, open a connection to Google. If Alice is logged in, she'll have a cookie that represents her session with Google, and the browser is going to put that into the package that goes to Google. So when Google receives it, they'll know it's Alice coming to visit because that cookie will be there. Okay. Now, what the adversary wants to do is steal that cookie. If I can steal the cookie, then I can put it into my own traffic, and then I'll be logged in as you. So that's called session hijacking. So I just steal your cookie, and now I'm logged into you instead. And we'll talk more about cookies later, and you'll also see them in assignment 2. But that's sort of the rough idea of how cookies work. Okay, so what I'm going to assume is that the JavaScript's running, and Alice is logged into Facebook, Google, something that the adversary is interested in stealing the cookie for. Okay. Now, the cookie is going to get dumped at the start of this packet. The actual request will go on the end. The request is in purple. The adversary controls that. So they're allowed to ask for whatever file they want or whatever. Let's just think of it as a file. So they're going to put a file name there, and they can control exactly what that is. Okay. The cookie value they don't see. The browser puts the cookie value there, so they don't know what the cookie value is. And it's all wrapped in SSL. So it goes in the tunnel, and so they can't see the cookie or the request. They know what the request is because they made the request, but they can't see it from the outside because now it's inside of the tunnel itself. Does that make sense, the setup? Yeah.
How they access to how attacker access to the cookie?
So the attacker does not have access to the cookie. So
Also, how steal like a token from the
how to steal the value that's sitting here?
yes.
So they can't steal it because it's in the tunnel. Yeah, so the browser puts it there. Yeah, I wish I had a mouse. I don't know why it's not working. Otherwise, maybe I'll just do it from here. So this is a secure tunnel. Yeah. So everything that goes through here, the adversary can't see. Yeah. And the cookie is put there by Alice's browser. So the adversary creates the request. The browser just puts the cookie at the front of that request and then puts it in the secure tunnel and sends it off. Yeah. So the adversary knows that the cookie's there. They know where it is in the packet, but they can't see it directly because it's encrypted. Does that make sense?
And this is through the website page, which presumably the attacker is on and has access.
So it's slightly different. Remember when you go to, like, say, Wikipedia, you can load an image from another website. So the server here is whatever the JavaScript is pointing at. Like we'll say, go to Google and get this image. Then the server there is Google, even though Alice isn't on the website Google. They're on a different website. Does that make sense?
Okay, so like the JavaScript that the attacker controls is like one of the sub things that are on the actual website.
Exactly. So she's on some website, either the adversaries or somehow the adversary gets JavaScript running on that website. The JavaScript is able to open a connection to third-party websites, any website. Yeah. And if she happens to be logged into that website, then her cookie's going along
So
for the ride.
Does Alice see that you went on Google and got that image?
So she knows what the request is because she made the JavaScript issue it. But from this, all she knows is she'll see a packet going to Google, and that's all she'll know.
She won't know what website is she's being led towards or something.
She has to know that it's going to. So the adversary has to know that it's going to Google because
The
that's.
adversary, but what about the user?
It's the same thing as if, like, say you know when we opened up TSN and it opened up a bunch of
Yeah,
connections.
you'll see it there.
Yeah, you would see it there if you
But
looked.
If you don't look there, you won't.
If you don't look there, you won't know it's happening.
Oh, okay.
Yeah. Okay, so anyways, this is like kind of a setup that's used. There's a bunch of attacks, Beast, Padding, Lucky 13, Poodle, RC4, that all use this kind of same setup. This one's called Crime, and they all work slightly different, and they exploit different vulnerabilities in the crypto. But I like this one because it doesn't require you to really look at the crypto itself.
Beef is one with Kali Linux, I think, that where you can do stuff like this.
Yeah, I think all of them are in
Yeah.
Metasploit. Yeah.
Yeah.
What is the exactly cookie? Is it a token? For example, when user try to log into the website and the server give the token, access token to the user, and then the attacker use the token to send a request to, like, for example, to the.
Sure, I'll explain it to you. So first off, we will have lectures on this later. It would have been convenient to have them before this. This is what happens. You go to a website for the first time, never been there before. There's no cookies or anything like that. Then you log in, you put your username, password, you press enter. Google says, okay, now I know who you are. Yeah. And then what it will do is it will create a random value and it will store it attached to your username. So say Jeremy Clark, pulpspy@gmail.com. This is the cookie value I gave him. And you might have more than one if you have more than one device. And then it's going to send it back to you. And your browser is going to take it and it's going to store it in a cookie jar, as they call it. And then every time you go back to Google, the browser is going to go through the cookie jar and say, do I have any cookies that belong to Google? It will find that cookie and it will put it in the front. Then it will go to Google. Google will look at the cookie. It will go through its database and say, oh, I recognize that cookie. I gave it to Jeremy Clark. Therefore, it's Jeremy Clark that's here. So I'm just going to log him in. I'm not going to ask for his username password.
But there's also some type of tracking stuff besides that it does, right?
Yeah, that's right.
That's why there's laws where you have to prompt to accept the cookie.
Correct.
Yeah.
Yeah. So we'll talk about that later. Yeah.
And Professor, how we can prevent this?
Prevent which, sorry, exactly, like having cookies or?
Prevent the cookie that we store, like if someone else try to use it, like somehow.
So you can either turn cookies on or off. So there's some finer grained control. In assignment 2, you'll use this Ghostery app, and that's what it's doing is it's trying to give you finer grained control over the cookies. But this is called a cross-site request because the website that you're on and where the cookie's going are different. And cross-site requests are you can turn off cookies or you cannot turn them off. That's basically your choice. And they're used for lots of good things too, like single sign-on and there's a million things. A Facebook like button on is CBC News or whatever. Like everyone uses cross-site requests everywhere. And so you can't really stop this from happening. But there shouldn't be a problem. Like right now, at this point, there's no problem, right? The adversary can't see it. It's in the tunnel. Yeah.
So if we check the customer IP address, if we like put the IP address in the cookie,
The problem with IP addresses is they change. So like, say I'm on my phone and I'm driving around, I'll go from one cell tower to another, and now I have a completely new IP address. So you don't want to make the person log in every time.
Okay, so if we put the IP address, then a user every time has to log in again.
Yeah, every time you change your IP address, you would have to log in. And if you share the IP address with other people, it might be, you could end up in a scenario where they're logged into your account just because they're on your IP address. Yeah, so IPs are, it would be a way of doing it, but it doesn't work for that reason.
That cookie edit on a packet, right? Sir?
It's on a packet, or
Yeah, on a packet. I mean, the request packet.
yeah. So it when you don't have cookies, there's no cookies. This, it always starts with the server. So the server will say set header. In the header of the response, it will say set cookie. Then your browser will remember it. Now that your browser has a cookie, then on every request, it's put into the header of the packet.
Just one time.
It goes every time every packet you send to Google, it will go just in the header. So if the packet is like long, it's not going to repeat it. But every time you throw something at the server, it's going to put that cookie in again. Yeah, okay. Yeah.
So, Professor, if we put the IP address and in the cookie for the user, and someone else try to use the cookie but with a different IP address, so we can prevent this attack. But the drawback is user has to log in again.
Yeah, so every time you change your IP address, the server wouldn't believe that you're the same person. Yeah. Okay. All right, so far there's nothing wrong with this picture. It's fine, it's secure. And this picture is the picture that we have today. But there was one flaw in the encryption that was used that led to a problem with this setup. So there were some protocols that use compression in addition to encryption. So the idea was that you would first compress the data, then it would be smaller, so that's better. Then you would encrypt it, and then you would send it. And then the other party would uncompress it. They would decrypt it and then uncompress it. Okay? This wasn't really a big thing in HTTPS. It was in TLS, but it was used more when you do TLS over UDP instead of TCP. So this sort of datagram thing. There was a protocol called Speedy, which no one uses anymore. It used it. But anyway, so this compression was sort of around. It wasn't, not everything was vulnerable to it, but some variants of TLS or HTTPS were vulnerable to it. Okay, so it wasn't like a widely thing. Some of these other ones like Beast and Lucky 13 were more widely applicable, but this attack is easier to understand, so that's why I'm focusing on it. Okay, so Mallory here is the adversary in the middle. She basically has two knobs that she can control. The first thing is, in that request, she can ask for anything she wants. Okay, so she can go to Google and she can ask for, just think of it as a file, like a file name of an image. She can set that to be any file name she wants. Maybe that file doesn't exist, then she'll get an error message that says 404 doesn't exist. But she can control that text. Okay, she can make the file name anything that she wants. And the second thing is, you might recall from last lecture, if you have data and you encrypt it, what happens to the size of the data?
Same.
Stays the same. Okay, so encryption is length preserving. Okay, all right. So using these two facts, we're able to attack this system. How do we do it? So first, let's think about how compression works. Let's say I have a picture and I want to compress it. Actually, let's say I have two pictures. One picture is like a very simple landscape, and the top 2/3 of the picture is the sky, and the sky is crystal blue, and the sky is almost the same color all the way through that picture. Is that a picture that you think would compress well?
Yes.
Yes, and why?
Because the similar criteria, like the similar pixel.
Okay.
Blue sky, all the blue. So if you compress all together,
Yeah, so instead of saying this pixel is this color, this pixel is this color, this pixel is this color, I can say the next 1,000 pixels are all the same color. And that's a lot smaller to send, okay? So the main thing with compression is repetition. If the data has repetition in it, it will compress well. If it doesn't have repetition, so what's an example of something that wouldn't compress well? So the extreme example would be completely random data. So if you have data and you, like say it's a picture, it's like static, you just generate it at random, it will not compress any more than it already is. Okay, so random data doesn't compress. Okay, so what the adversary can do is in the request, they can start guessing at what they think the cookie value is. Okay, so for example, they might put E33A as a guess. Does that value show up in the cookie somewhere?
Yes.
It does, right? Is that going to compress well?
Yeah.
Yes.
Yeah, because it's going to be repetitive, right? So there's going to be 2 occurrences of that byte pattern. Now, let's say their guess is wrong. They guess 093A. That's not anywhere in that string. Is that going to compress well?
No.
It won't compress well. Will they be able to tell whether it compresses well or not, even though it's encrypted? They will, because it's length preserving, right? So if it compresses well, it's going to be shorter. And then when you encrypt it, you're still going to know what length it was. Okay? Yeah.
But if the cookie is, like randomly generated, wouldn't that just be repeated?
Yeah, so the cookie itself will not compress well because it's random. But what I'm doing is I'm repeating, so I have what's here, and I'm also repeating it here.
I mean, more like just like in terms of actually guessing the cookie this way, it feels very inefficient.
Correct, yeah, it is.
Very unlikely to guess it.
Okay.
Due to the fact that the cookie itself is random.
Sure. So you will have to do sort of an exhaustive search. You're going to have to try every possible byte thing. But normally you would have to do an exhaustive search over this whole string. The main trick here is I can just guess, say, the first 2 bytes. Once I get them, I know them. Then I can just guess the next 2 bytes and then the next 2 bytes. And so because I can divide it up, then it becomes a much faster algorithm for solving. So it still is something that you would be opening like 10,000 or 100,000 connections in order to do this attack. Yeah? So that is correct. Yeah. Okay, so what we do is we just throw guesses into the request. If they happen to match the cookie, it will compress better, and we'll be able to see that because the length of the ciphertext will be shorter. Then we know we're getting close. And then through trial and error, we'll basically keep putting guesses in, and every time it compresses well, we'll kind of keep it. And then they showed that eventually you could extract the value of the cookie itself. Okay, but again, it takes lots and lots of traffic to do it. So these are the limitations. So first off, it's a powerful adversary. They're a man in the middle, and they have some JavaScript running on a website, which we call cross-site scripting. They can only steal secrets that are beside text that they control. So you need like this setup where there's a secret and there's text that they control and they're side by side. So it works for stealing things like cookies, but it doesn't necessarily work for other stuff. And there's lots of trial and error, and it's going to generate a lot of traffic. And because it's generating a lot of traffic, intrusion detection, that type of stuff, or the browser, Alice just notices the website's going crazy and her computer's slowing down, the fan's spinning up, whatever. So she closes the tab, then the attack is over. So it's not the most practical attack, but it should not be possible to do this in TLS. It should protect against this.
Is it resolved now? Or?
Yeah, so then they removed compression, basically. That was the resolution. Yeah. Okay, other questions about this? Okay, so there's a whole bunch of crypto attacks. If you're super interested in it, you can, well, first you could take 6120 with me. We talk about a couple more that we don't talk about here. And you could do a project or something on it. But essentially what we have is we have attacks on the crypto itself. So we didn't really go through all of them, but you saw crime, which was one of them. You can see there's a bunch of other ones. And then there's other attacks that are more based on the implementation itself. So Heartbleed was a problem with the implementation. And then there's some attacks that the side channel attacks were based on the implementation as well. And then there's other attacks too that are sort of in that vein where you're kind of attacking the crypto, but there's a bug in the implementation at the same time. And because you can stack those 2 things, then you're able to break into the tunnel itself. Okay.
So all of these are not possible anymore?
Correct, yeah, yeah. Unless if you get downgraded to one of these older versions. Yeah.
And that's not.
But downgrading itself isn't vulnerable, yeah. Yeah, so everything is fixed, more or less. Yeah.
For now.
Yes, yeah. Okay, so questions about this side of the tree? Okay, so we spent the least amount of time here just because it's a lot of crypto to like go through this part of the tree, but at least you get a flavor for what's going on. Okay, so we've looked at what can you learn from outside of the tunnel. We've looked at could you break directly into the tunnel? And we saw, yes, if there's a flaw in the software, you could. If you could steal the key that's used, you could do it. Or if you could attack the crypto, there's some flaw in the way the encryption's done, then you could break into it. The third idea that I have is, what if I can get the tunnel pointed to me instead? So I'm the adversary. The user thinks they're going to Google. They see they have a secure tunnel. They're dropping their packets into a secure tunnel, but it's ending at me instead of ending at Google. Then they're just delivering their traffic directly to me, and I can read it. Okay? So user, they can see the messages are going into one end of the tunnel, but they don't know where the tunnel ends. Okay? So where does the tunnel end? What does it mean to end a tunnel? So there's a bunch of crypto that's involved, but this is the only piece of it that you need to know. In order to make these tunnels, you need to have what's called a key, a cryptographic key, and it's going to be a secret key and only you know it. So Google has a key, Concordia has a key, every server has a key, okay? Now, keys have sort of two components to them. There's the secret key that you know, and then there's the public version of your key, which you can publish, okay? And so when people send you traffic, they use your public key and you decrypt it with your private key. Anyways, it doesn't matter, okay? So right now we have this public key value. And if I can get Concordia's public key, then I can make a tunnel to Concordia. If I can get Google's public key, I can make a tunnel to to Google, okay? That's the only requirement itself. So you don't have to worry about any of the other crypto itself. This problem just completely reduces to, if there's a telephone book with every server and every public key, then there's nothing you can do in this case. Yeah.
Doesn't that mean I have to compromise the certificates authority guys?
Yeah, we'll get there. Yeah. Okay. So if you can solve this problem of knowing whose key belongs to who, then you can solve the whole thing. Okay. Now this is a hard problem because your computer, like maybe you updated it 2 weeks ago. Okay. And I just made my website yesterday. Right? So there's no possible way you could know what my key is unless if you go asking someone else what my key is. Okay? So just keep that in mind. That's one of the reasons why this is tricky. And this needs to work for every website, even a website that was just created 5 minutes ago. Okay? That nobody in the world, you're the very first user in the whole world that has ever gone to this website. You somehow have to know that the key that you're getting is the right key for that website. That's the problem that we're trying to solve. We call that problem PKI, public key infrastructure. It's just basically mapping people's keys to their identities. Okay, so how do we solve it? So certificates were mentioned. What's a certificate? Anyone know?
Like, I guess,
Yeah.
that makes it like officially where you want it to go.
Okay, yeah. So certificate's going to have, it's,
That where you're going is like officially the real thing.
okay. And more specifically, it's going to be about the public key of where you're going. Yeah. Okay. Yeah. So what a certificate will have in it, it has a bunch of stuff. We'll see some examples, but the two main pieces of information it has is where you're trying to go. So let's say concordia.ca, and then there'll be the public key itself. Okay. It's a digital document. And so when you go to Concordia, they'll say, here's my certificate. And if you go into the certificate, you'll see the URL and you'll see the public key itself. Okay. Now, if I get this, say I go to Concordia and they send this back to me, does that solve the problem? Do I now know that that's their public key?
You have to prove his authenticity?
Yeah, so let's say there's an adversary in the middle. Let's say that is actually Concordia's public key, but there's an adversary in the middle. What's the adversary going to do? They're going to switch that public key for their own public key. Yeah? Yeah, so you have no idea. It's just somebody sends you something on the internet that says this is Concordia's public key, right? It doesn't tell you anything because the adversary could have sent it to you. Okay? So we haven't solved it yet. So how do we get around that?
Just sign it.
Okay, so what we're going to do is we're going to have somebody sign this, and if they sign it, a third party, and if they sign it, then the adversary can't change it because it's signed. Sorry?
CA?
Yeah, so a certificate authority is what we'll call them, okay? So there's going to be this company, call them Global Sign. They're a certificate authority, and they're going to sign this information, okay? So now if the adversary tries to change the Concordia's public key, the signature will no longer be valid, right?
Yeah.
Okay, so that solves the problem.
That's just another signature.
You have to have a copy of all the trusted certificate authorities on your computer.
Okay, you don't. Okay, that's one way of doing it, but what you do need is somehow I have to verify this signature.
You have to have it registered.
Yeah, what do I need to verify that the signature is correct? I need Global Sign's public key. Yeah? So how do I know that the adversary didn't just sign this document with their own key? Right? So now the adversary is changing the key, Concordia's key to their own, and they're changing Global Sign's key to their own, and now they're giving it to you. Okay, so,
That could just go on forever.
and it could go on forever. Yeah, exactly. That's exactly right. Okay, so what did we do? Did we solve the problem? We didn't. We pushed it. We said, I don't know what Concordia's key is, so I'm going to introduce certificate authorities, but now I pushed it to, I don't know what Global Sign's key is. Yeah, so I didn't actually solve it. Okay, so this is the issue. How does Alice know the public key of the certificate authority? And then let's say that Alice has some way of knowing that. I don't know what it is. Call it method X. Okay? Somehow she has method X, and with method X she could establish what the public key is of Global Sign. Then she could also use that same method to figure out what Concordia's key is. And so then she doesn't need a certificate at all. Right? What's the point of a certificate? If she can figure out Global Sign's key, she could figure out Concordia's. We don't even need Global Sign anymore. Okay? So that's the first question. The second issue is that Global Sign signed this. Okay, let's assume that somehow that worked and you can tell that Global Sign signed it. There's no doubt about it. That means Global Sign themselves figured out what Concordia's key was. How did they do that? Right? And however they did that, why can't we do it? Again, I don't need Global Sign because they have some way of doing it, so I could just do it myself. Okay? So these are two questions. They're tough questions, but we'll try to answer them. Okay, so let's start with the first one. How do you know the public key of the certificate authority? So the answer was suggested already. I go to the Apple store, I buy a computer, never turned it on, never been connected to the internet. I turn it on for the first time. A bunch of keys of certificate authorities are in my computer already. Okay, they're just there. They're there by default. Apple put them there. They're called root certificates, and they're on my computer when I get them. Okay, so it just comes hard-coded with certificate authorities and their public keys. You can go and look at them. Let's see.
I looked at it online.
I think they moved where they are in the new operating system. Is there passwords? Huh. So it used to be called Key Store. I should have looked to see. Anyways, I have a slide picture of them, so we'll just use the slide. So I'll have to figure out where they moved it
You got a
to.
new computer?
No, just new operating system upgraded. How many certificate authorities do you think your computer comes with? If you don't know. If you know, don't say the answer. Like rough guess. Like, I'll give you two numbers. I'll give you 50 or 500.
500. 50.
Okay, so 50 or 500, probably more like 50 kind of thing. Okay, so it turns out, or it could be like 5. It turns out it's about 50. Okay, now that's a pretty big number, right? Some people might say, oh, maybe there's 3 certificate authorities or 10 of them. Okay, but there's about 50 of them. Some of them have multiple keys, and some of these companies are owned by other companies that are on the list. Okay, now I know it's scrolling around really fast, but there's things like GoDaddy. Have you heard of GoDaddy before?
Yes.
Okay, have you heard of Amazon before? Have you heard of Entrust?
Yes.
So one yes, but most no's. GeoTrust, Global Sign, TrustCore.
Most of them were.
So most of them are probably companies you never heard of. Yeah?
How does this work for like international?
So they will be international too. So this is not, even though some of the ones I'm saying are American companies, you recognize them as US, this is like for any person in the world. Yeah. So a bunch of these companies will be anywhere in the world as well. Yeah. So this list should cover the entire planet. Yeah.
Will it ever need updating? Or like, are there ever cases with new certificates?
Yeah. So new certificate authorities new root certificates are introduced sometimes, but how do you change this? You have to do a software update. So you cannot make a change to this list without a software update. So we have a different mechanism for introducing brand new CAs that we'll see in a second. But generally, these roots are pretty stable over time. You'll also notice there's an expiry date. It's sort of scrolling fast, but some of them are like not that far in the future, but a lot of them are like 2045, 2029, 2030. So there are things that are going to last 20 years.
And what happens when they expire?
When they expire, you got to get a system update before then. Otherwise, you won't. Anything that chains back to that, what your browser will reject and say, I don't know what that certificate
if you
is.
compromise this folder and write your own root certificate, then it's dangerous, right?
Yeah, so let's say that an adversary can just write one certificate into this root store. Then what they can do is they can generate a certificate for any website on the planet. So what they'll do is they'll see that you're going to Google. Google will say, here's my real certificate. They'll replace it with their own certificate, with their own key, and they'll sign it with the certificate that's in your store, and your computer will be like happy. It'll say, great, I know what that certificate authority is, okay? So this happens. So this is what, for example, let's say you install antivirus software or a VPN sometimes. What they'll do is they'll write a custom certificate so that they can be the man in the middle. They're doing it for your protection, right? They're looking for malware that's coming down over HTTPS, but they need to man in the middle all of those connections to do it. The way they do it is they put it here. Organizations will do it as well. So let's say you go to a company issues you a computer, they'll slip their own root certificate in. Now they can monitor any traffic that's going over encrypted channels as well. Yeah. So these are called interception proxies. And
Even if you, but if you reinstall the operating system, it would go away.
if you somehow change your operating system back, then it would go away. So then here's a story, I'll tell it now. There was a security researcher, and he went to one of these big fairs like the RSA like conference or something like that, and there's all these booths, set up with different people that are selling things. And lots of people sell the hardware, like a server rack like a server racked server. What am I trying to say? But anyways, a mounted server, you put it in your rack, and then now you plug your gateway in through it, and it's going to do this interception for you. Yeah. And so he was going around, and there was lots of companies selling these things. And then he went to a couple companies, and they were saying, "Oh, this ours is really good. It's way better than the other product because if you use our product, you don't have to change anyone's operating system. You don't have to change their root store. You can use our interception proxy, and it will just work with any computer." And the security researcher says that doesn't make sense. Like it's not. You have to put a root certificate into here. There's no way that works. So they bought one. They didn't know they were security researchers. And then they kind of took it apart or reverse engineered it. And what they realized is that one of these companies had given them basically like a certificate for doing this. And so that's how they were able to do it. And that's like completely illegal and against all like browser policies and things like that. And so then once it was discovered, then the certificate authority that had done that for this company got in trouble. I think they got their root certificate removed from the store. Okay, so these are root certificates. Questions? Yeah.
Who regulates it? Like,
No one. So there's a loose regulation, which is there's something called the CA browser form. It's voluntary, so there's no laws or anything like that. But the browsers, the major browsers, they're the ones. Either the operating system or the browser is going to choose these root stores. So the root store will be given to you. I'm on a Mac, so Apple chooses it. If I use Chrome, Chrome will ask my operating system for it. If I use Firefox, Firefox will do it itself. So sometimes your browser comes with its own root store. Sometimes the operating system comes with it. But anyways, everyone who makes these root stores, they came together and then they tried to get as many, there's an open invitation to any CAs and they'll come as well. And then they'll discuss things and they'll set guidelines and things like that. But if someone doesn't follow it, like the punishment basically is you'll get kicked out of the root store by the companies themselves. So it's not like a police or law enforcement thing.
Is it the same ones for all different operating systems, like Windows or Linux?
Yeah, so every root store must look almost the same. Otherwise, some websites, like imagine there's a website that you could only go to on Windows or you could only go on Apple. We don't want that. So either the root stores are identical, or sometimes you can have cross certification where, let's say there's a company that's issuing certificates and they get a couple of these root certificates to vouch for them. Then they might have one on Windows and they might have a different one on Apple. But by and large, it's going to be the exact same list across all of them. Yeah. Yeah.
Firefox roots, for example, is it placed in another place or is it aggregated in this list?
No, it will be put in their browser itself. So like in the software for the browser. So it'll be distinct from the list itself. Yeah. Okay. So there's a lot of CAs, 50 companies, a lot of them you haven't heard of. Why do we care that there's 50 as opposed to 5? Well, the main thing is, this is the most important thing. Any CA can issue a certificate for any website. Okay? So there's no notion of like, oh, Google only uses themselves as their CA. Right? If some weird CA that you've never heard of issues a Google certificate and they're in that list, your browser is going to accept it just like it's the real Google certificate, right? Nobody knows, you don't know anything other than the list of CAs in your root. That's almost true. It's not quite true for Google because they do special things, but we'll get to the special things later. Okay, so there's no notion of like these CAs can sign for .coms and these CAs can sign for US companies. There's none of that. So any CA, so you compromise one of these 50 companies, then you can issue certificates for any website. You can get the tunnel pointed at you if you're in the middle, if you can do that. But it gets worse. So the way the web really works usually is root certificates don't really sign Concordia's certificate directly. The reason is because they're supposed to last for 40 years or 20 years. You don't want to keep these things on a computer because every time Concordia would come, they would have to get that signing key and they would have to sign, and that's very vulnerable. So what they'll do instead is they'll issue a middle certificate. So Concordia's will be signed by the middle certificate, and the middle certificate will be signed by the root certificate. And the root certificate will only sign the middle certificate once a year. So once this will last for a year. Next year they'll go back and they'll have to get the root certificates like literally stored like in a safe where you need 5 employees, to all put their fingerprints. There's an article on Moodle about VeriSign, one of the big ones, and it kind of walks you through the procedure of how they do this signing. So it's like really like top secret stuff. But anyway, so once a year they'll go in, they'll dig out the root certificate, they'll sign a bunch of middle certificates, and then they'll use the middle certificates on a day-to-day basis. Yeah.
Intermediary guys, are they like fixed in number like the roots, or do you have like?
Great. So the root signed it. So the root knows. So from the root's perspective, they know all the intermediaries that they sign certificates for. But from the user perspective, do you know who the intermediaries are?
No, but once you know it's from the root,
Yeah.
you automatically trust.
Correct. Okay, so first off, you will trust it because it chains back to the root, but you won't see it until you go to a website that happens to use it in the middle. Yeah? So you won't see it until then. Yeah.
When you go in the, like, in the browser and you look at the certificate,
Yeah.
it'll have all this information?
Yeah. So let's do it. So I can go show certificate, and you'll see here, this is the 3 certificates. So
the middle one is the global sign, that one?
yeah, so the middle one, the global sign one in the middle here is the intermediary. And then you'll see, you can't really see the resolution's not good, but see how it's sort of like gold and it says root certificate? That's like the thing that's on my computer. So if I go back to the list of all the roots that are on my computer, then it will be there. Yeah. And then the certificate itself, you can see all the information inside of it. And so there's more than what I suggested, which is just the name and the public key. But anyway, so there's Concordia. The public key value is here. So this is the public key itself. And then there's a bunch of other stuff. We'll look at some of these fields over the next lecture. But yeah, we won't talk about all the fields.
So there are companies that are specialized in signing, right? I mean, that's Global Sign. It has its own intermediary and stuff like that.
Yeah, so certificate authorities are the companies that issue certificates, and they're specialized in signing certificates. Yeah. Okay. But there's a slight thing that you're sort of hinting at. Is the intermediary the same company as the root? So we saw Global Sign in the Concordia case, it was the case, but is it necessarily the case? The answer is no, okay? So there could be a bunch of intermediaries that are not roots, okay? So if I say there's 50 CAs in the world because I see 50 roots, that's not actually true, right? I know there's 50 root certificates, but there could be another 50 intermediaries. When would I see them? I will never see them until I go to a website that happens to use them, or the root certificates tell me who they are, and they don't. They don't go around saying who they've issued intermediaries for. Okay? So intermediaries are sort of complicated, and if you want to figure out how many there are, you can't know that. It's not a file on my computer that I can go and look at. Okay? I can estimate it though. So a couple ways I can do it is, one thing is I can go to every website on the internet. Okay, that sounds kind of crazy, but if we're using the old IP addresses, IPv4, it's doable in a couple days. So you just go by IP address, you go to 00000, say I want to talk HTTPS, and it will say, I don't know what you're talking about, or it doesn't say anything, or it says, great, here's my certificate. Then you write down, when the site sends you a certificate, they send you the whole chain, because you need to be able to chain it back to your computer. So then you write down the intermediary, then you go to the next IP address, you go to the next IP address. And so there's some tools that researchers have made that are very fast at doing this. But you can't do it for IPv6. There's too many IP addresses now, you can't possibly traverse them. Yeah.
How long is usually the length of the chain? Is it
So it's usually 3, and there's path restrictions you can set in the certificate itself. So when this person issues a certificate, they can say, you're allowed to issue certificates, but they can only have one more path length. You can't issue another chain that issues certificates, kind of thing. But 3 is typical, but it's not a rule. It could be any length. Yeah. Okay. And so when there's another project called Certificate Transparency. It grabs site certificates under certain conditions, most conditions now. It may or may not include the chain back. So you could try to look at this project to see all the intermediaries, but not every site certificate is in this project either. Okay, but based on these 2 things, we can estimate there's probably another 200 companies that some people say up to 600. So there's somewhere between 200 and 600 companies that are able to issue certificates. Now, let's say you're an attacker and you have the choice of compromising a root certificate or an intermediary certificate, it really doesn't make a difference. In either case, you can issue any certificate for any website that you want. With the root certificate, if you get caught, it's going to be a little harder to get you off of the system than if you have an intermediary. So you might prefer the root certificate for that reason. But the power that you have with an intermediary and a root are basically the same. Okay, so attacker doesn't care. For the purposes of breaking HTTPS, they don't really care if they get an intermediary or a root. As long as I can get one of the two, then I can break any SSL connection. Yeah.
Intermediary not specific to a particular website?
Also not. Yeah. So any intermediaries are CAs. And any CA can issue any site, certificate for any site. Okay. So an adversary that breaches one CA it doesn't matter if it's an intermediary or a root. Then they can issue a Google certificate, Facebook certificate, whatever they want to. Major websites have ways of protecting themselves. So if you're Google and you own a browser like Chrome, you can hard write into Chrome what your certificates are, or maybe the name of the certificate authority that you use. Then if Chrome ever sees a Google certificate issued by any other certificate authority, what it will do is it will actually phone home to Google and say, I found this in the wild, and Google will investigate. And CAs have got caught that way. So there are attackers that have breached CAs successfully, but they went out and they issued a bunch of Google certificates because they wanted to break Google traffic. And then one of the users that they attacked was using Chrome, and Chrome was smart enough to know that's a weird certificate. And then it called home with Google. So then Google had a copy of it, and then they looked into it, and then they were able to see that there was a compromise of those CAs. You can also tell Google what your certificate is, but you have to be big enough to be able to go to Google and say, Facebook can go to Google and say, these are my certificates, put them into Chrome. The other thing is you can advertise what CA you use on your website, but this is trust on first use. So the person who goes to your website the first time, they have no idea what CA you use. But if you're able to form a secure connection the first time, then they can download what CA you use and remember it for future connections. So we call this pinning. Pinning's a little dangerous though. If you say, I'm always going to use DigiCert, okay, and DigiCert goes out of business, all the browsers that remember you only use DigiCert, they're not going to accept any other certificate that you send. It's going to look like an attack, okay? Or DigiCert could jack up their prices and you're stuck, kind of thing. So pinning is dangerous to do, but it's something that you can do. And then when Google goes around the internet and crawls your website, they'll see, oh, this is the certificate that you want, and then they'll put that into Chrome as well. But
Google can do that, not other.
exactly, Google can do it for themselves. Microsoft, Apple can do it, but Concordia can't do it. We don't control a browser or things like that. Yeah. So these are special rules for the top 100 companies, but that don't apply to the rest of the web. Okay. And then there was a question about where these CAs are. So these are all over the world. Okay. So they cover all the different countries. There have been problems as well with CAs that are aligned with foreign governments that have done bad things. And so there's also the question of, could a government put legal pressure on a CA? So let's say the government wanted to intercept traffic. Could they go to a CA that's located in their country and say, give me your keys? And then they would be able to break it. So there was one telecom that got in trouble in, I think it was in the UAE, and they were putting malware on people's phone that was state-sponsored. So they got in trouble for that. That was a while. And then a few years later, someone realized that, they have a certificate in the certificate authority store. And so then there was a big protest, and they tried to get it removed from the certificate authorities store. And I think it wasn't successful in the end because they were too big of a telecom. Okay. Questions about any of this so far? Yeah.
Actually, one curious about the slide of OS, operating system, and browser like Microsoft Edge or Firefox or Google Chrome. If they violate
Yeah, so
Is there a number?
they have a lot of power from a whole bunch of angles. So the fact that they control the root store probably doesn't give them much power, but the fact that they control the browser and they can see every website that you go to, they control the most popular website on the internet, which is Google, the search engine. And a lot of people will find websites going through Google. Lots of people have Google accounts. They're logged into their Google accounts at all times, right? And so it puts them in a powerful position, for sure, for tracking users.
Government have some sort of rules for this?
So yes and no. Yeah, they do. Actually, they do specifically. So like in Canada, it was mentioned like now you go to websites and there's that thing of like, do you want to accept cookies and allow cookies and things like that? That was a government initiative. So the government said you have to do that. And
Government laws controlled by
yeah, so you mean that Google controls the government?
I know actually government controls the like
Sort of, yeah. So the government passes laws, companies who are operating legally in Canada. So there's lots of websites that just don't care what the Canadian law says. But if you have a company that does, then they'll follow the Canadian law and then they'll implement some of these things that are meant to curb tracking. Yeah, but you can still legally do lots of tracking. And if you get the user's consent, right, to like if you just go allow all cookies because you just don't care, then it doesn't matter, then they can track everything. Yeah.
Who gives the CA the signatures? Like who's the top?
So the operating system will allow them to go into the root store. So that's where the permission starts. So Apple was you're a new CA.
Who issues the CA's signature?
To the root themselves?
To the companies, to the 50 companies.
Yeah. So the 50 companies issue it themselves. So they actually have what's called a self-signed certificate. So they just say, this is my key, I sign it
Don't they need an
myself.
approve from
Yeah, so-
authority or something?
So Apple has to put their root certificate into everyone's computer. So that's where they get their authority from.
Like for example, in this example, you said they put some malware in the phones. And
Yeah.
So how they removed who removed the permits from them?
Oh, I see. So all the browsers would have to agree to do that. So it's one of two things. So if it's an intermediate certificate,
Yeah.
the root certificate could revoke it. So whoever the root
Okay.
was that signed it, you could convince them to get rid of it.
Who could revoke the root certificate?
But the person that revokes the root certificate is the operating system. So
Okay.
you have to go to Apple and say, get them out of the root store. And
Apple
Apple would have to
knows.
issue a software update. And then everyone who updated their software would now not have that
You can't
certificate
just
anymore.
delete it yourself?
You could delete it yourself too, yeah, if you wanted. But the company or Firefox or whoever's putting the stuff there, they're the ones, yeah? Okay, yeah,
Is it possible for a country, let's say Canada, for example, to say, okay, root CAs A, B, C, D, you will pressure them to like, we want your keys so that we can check everything going in and out of Canada, for example.
exactly, that's the point I was trying to make here, yeah? So it might be the government is a CA. I didn't say that explicitly, but like, for example, Department of Homeland Security in the US, they did at some point, I don't know if they still have it, but they have a certificate authority.
Is it possible to know if who issues, like who is the person behind the root authority?
Not really, I mean, they're public, like you see a digital document that's signed and you see a business name. But someone should know, like there should be policies, and it was issued by some root certificate. And the root certificates, everyone knows who they are, like they know physical addresses and things like that. So they could go to the root certificate and figure it out, yeah. Unless if it was breached. So it might have been issued in a breach, right? And so then the root doesn't know about it either. And so that's happened as well, yeah. Yeah,
So I tried to find the keys on my phone, I couldn't, I don't know where it is.
your Android?
Yes.
Okay,
I
yeah.
don't know where it is. But it is safe to say that my phone, mobile service provider has some CA, right? Let's say Virgin or.
Yeah, perhaps. Yeah, they're the kind of big tech company that could have a CA. They wouldn't strictly need it, but I wouldn't be surprised for sure.
And how long does it take to some reports like this, like one of the one that you showed about malicious CA or breach CA gets out? Like it's about months or years.
Like how long does it take to kick them out?
To know what? Yeah, I mean,
Or to know that someone got kicked out? So like you would have to rely on the press or like the tech journalist or someone like that to tell you that it happened, or you'd have to be in the loop. And the amount of time in the process for kicking someone out is something we'll talk about. It'll be next virtual class. But that's this topic of revoking a certificate. So, and revocation's a mess. It's, you'll see that like there isn't a good solution there. Yeah.
So I just wanna make sure I'm understanding, so like if I built a brand new website, I could get a certificate for it. It doesn't mean that the website I built is good or not, you know, I could be Eve, you know, it doesn't matter. It's just certifying that it's going where it says it's going.
Yeah.
And that if something changes, it'll have broken the certificate. That's all it's proving.
100%. Yeah. So if you go to a website and it's over HTTPS,
Yeah.
and you used to see the lock, but now we don't. But that lock doesn't mean it's trustworthy. It's a good website. People know even who the website is. It's not an endorsement. It's nothing. The only thing it means literally is that your computer's tunnel ends at whoever owns that domain. That's the only guarantee that you get. Yeah.
So
But people misunderstand that. People think it has to do with trust and things like that. Yeah.
if I don't get that certificate, then that it would be then I wouldn't be over HTTPS.
Yeah, so
Is that true?
your browser could, yeah, if you can't verify the certificate for whatever reason, then your browser won't show you HTTPS.
there is no rule about getting a certificate. I think there are some malicious or, I mean, illegal sites about copyright or stuff like that that it is
They can get a certificate. So as
it would be revoked.
it may be like if you, usually they would revoke the website itself, like they would take the domain name away from that person. But I mean, you could try to like revoke the certificate as well. But in general, certificates aren't set up to try and figure out if a site's legal or illegal or anything like that.
Pirates
And
back-
yeah, you can get the certificate before you put any content on your website. So as soon as you buy the domain, you can get a certificate for it right away. So yeah, so you don't know, the CA doesn't know that it's a bad website because they gave the certificate before the website was even there. They don't know anything about it.
So it comes with the domain.
So it comes with the domain, sort of. We'll talk about that too. So that's going to be a thing, like how you get it in the first place. Okay, other questions? Okay, let's take a 10-minute break and then we'll pick it up. Well, then let's go back to the lecture itself. Okay, so we had two problems that we want to solve with the certificates. We thought certificates solved this whole problem of now I know whose public key is whose. How does Alice know the public key of the certificate authority? The answer is she gets it on her computer, or it chains back to something that comes in her computer. And then we can say, well, if Alice can look on her computer to get Global Sign's key, why can't she look on her computer and get Concordia's key? So why don't we just put every website's key onto your computer if we're using that? Yeah, so there's too many and they change too fast. Yeah, so what we do is we put a couple on the computer and then we chain back to, and so it gives us the flexibility and it scales up to millions of web certificates and things like that. So that's the reason why we don't do it that way. Okay, now the second question we didn't answer though. How did Global Sign figure out what Concordia's key was? Right, so they signed off on that certificate, so somehow they figured it out. And however they figured it out, why can't we do the same thing? Okay. So they, who's they in that sentence? The yeah. So let's walk through this and try and reason it out. Okay. So I go and I buy a domain. I have like GoDaddy or someone like that. That's the domain registrar. So now I own this domain. I program the IP address of where I want my web traffic to go. It gets, everyone's DNS gets updated. So now you type in concordia.ca, you press enter, you come to my IP address. Okay, then what?
Like, with the domain or the GoDaddy, would they also give you like a public key or something?
Okay, so they could. So that would be an easy world to live in, where the domain registrar would do it. You saw GoDaddy on the list, so they do it. But do you want to be locked into having to buy a certificate from your domain registrar? Not necessarily. And other companies will maybe offer a better price or things, or you can even get free certificates now. And so there might be reasons why you wouldn't want to go with your domain registrar. Yeah? So then what do we think? How are we going to figure this out? So you're now another company, right? And I say I control concordia.ca. This is my public key. How do they figure out whether I actually control it or not?
Don't they all have like a unique, like ID?
I do, for sure, yeah.
That's the
Test you in some way?
Okay, so they could try to like visit the website.
that's the information.
Yeah? So that's similar, that's actually more or less what will happen.
Information, so name, details.
Yeah, so they could also like do the sort of human thing, like you send your business documents and that type of stuff. Yeah. So those are basically the two worlds that we're going to live in. And there'll be two different kinds of certificates that you can get. Three, technically. So there's going to be what's called an OV or an EV certificate. What it's going to do is it's going to try and bind together three pieces of information. So it's going to say concordia.ca is the domain, the public key, and by the way, this is Concordia, the University of Montreal. Okay, so like you know who your tunnel's ending at Concordia, the University of Montreal. Okay. The other type of certificate is a DB certificate, and it will only bind together the domain name and the public key value. Okay, so you'll be going to concordia.ca. You'll know that that key belongs to whoever controls concordia.ca. You will not necessarily know that that's Concordia in Montreal, as opposed to the other Concordia in Edmonton, as opposed to the other Concordia in the US, although because it's .ca, that might not be the case. Or somebody else who just registered that domain because it was free. Okay? So I don't know if this is the real Concordia or not. I just know that I'm going to this particular domain. So let's start with we'll talk about this process, and then we'll talk about this process. Okay, so the EV certificate is the thing where you pick up the phone and you call them and you try and convince them who you are, and they'll ask for some documents and things like that, and you'll go back and forth with them. If it's an EV certificate, this is the highest level certificate, the one that has the most validation. They call it extended validation. That's what the E stands for. They'll only give it to companies that have registered with the government. And the CA will be based into a country. So different countries will have EV certificates, but let's say it's in Canada. Then Canada, you'll have a Canadian registered business name, and the certificate will actually say it. So it will say this is the business number of this particular company. These are slow to obtain, as you can imagine. They are expensive too, because you have to go back and forth, and you have humans that are looking at it at the CA. But they're very secure, right? They really do check everything. The only like kind of main attack on this would be some sort of social engineering attack, where you pretend that you're Concordia and you make a bunch of fraudulent documents or things like that, and then you're able to convince them. So this has happened at least once, not for a certificate for the web. It was actually for signing code, but the process of issuing these certificates is exactly the same. There was someone who worked at Microsoft. So they were a proper Microsoft employee, but they were fired. And then they went to a CA, but they still had their like employee card and things like that. And the CA didn't know that they were fired. And so they were able to get a certificate using all their identification and all the stuff that they had just because they didn't know that. Yeah, so everything expires, and all certificates are about 1 year or 2 years, and then you renew. Okay, so there's two attacks here. One is, can an adversary get a Concordia certificate that doesn't affect yours, it's just now there's two certificates floating around. One's your real one, one's the adversary's. And then the other thing is, what if they compromise your key? If they steal your key, then they can also like use your certificate. Yeah? So in both of those cases, you want to get that certificate, or like if they steal your certificate, you're going to issue a new certificate, but you have to get the old one removed or revoked. And in the other case, you have to get the other certificate that's floating around revoked. So you're going to use revocation. I'll tell you about revocation later, but it's a whole process itself. Yeah. Okay. The EV certificate, it was like the strongest form. And so what browsers did is they changed the way it looks if you're going to a website that uses an EV certificate. Okay? And so what they would do is they would actually use green to indicate that you were on an EV website. And then they would also put like the company name as well. So you would see concordia.ca, but then it would also say, Concordia University or whatever the business name is, and it would use green. Okay? Does anyone?
That's before?
So this is before, so it doesn't work. It doesn't do now. Does anyone remember seeing this?
I don't remember.
Okay. If you did see it and you went to these, would you know why it's green?
No.
Would you care?
No.
If you went to one website that was green today and then tomorrow all of a sudden it wasn't green, would you remember?
No.
Be like, oh, that's weird. This should be green, right? Like, so basically people had no idea what it meant. It didn't mean anything to anyone. No one was paying attention to it or keeping track. So that's why browsers got rid of it. It just wasn't, it wasn't helping anything. But EV still exists. They just don't show it. I'll show you where you can see it
So
now.
what does the green color mean?
It just was more trusted, I guess, or green means go, kind of like a traffic light. I think that was probably why
But it
green.
doesn't mean that another type of certificate would, the other type of certificate, the DV wouldn't have this color, right?
Yeah, so the DV would just be a plain,
Alright.
like lock or whatever.
So it would be less trusted?
Yeah, so that was what they were trying to establish. So that this is more trusted because it's a business, it's registered and things like that. So it kind of solves the problem of like, is it a sketchy website in addition to just where the tunnel ends? So they were definitely, and they cost a lot more. People wanted value for their money. And so like if you pay $10,000 for a certificate or if you get one for $100, you want something to show for it. So we'll make it green. But just users didn't know, care, understand, track it. And so they eventually just got rid of it. There's an OV certificate. It's kind of like a less rigorous version of an EV certificate. So it will include the name of the organization. So like say Concordia, but it doesn't strictly have to be a business name that's registered with the government. So they'll do some lightweight checks on the organization name. So, okay, I have some examples. I'll go to DV first and then I'll go back. Okay, what's the problem with this? Let's go back to the EV. Okay, it's sort of slow to obtain, right? It might take a couple days, for all your documents to appear. We know certificates expire, okay? So imagine this is the scenario. You run a business, you're making $1 million every day selling something online, and you forget that your certificate's about to expire. You go to bed one night, you wake up the next morning, you have 1 million support tickets, and they're all saying, every time we go to your website, we get an error. Okay? You're not making any money anymore. You're now making $0 a day. Do you want to wait 3 days to get a new certificate?
No.
Definitely not, right? I don't want to wait at all. I want it in 5 seconds or in 30 seconds or something like that, okay? So there was a huge demand for, can we automate this process somehow? Instead of having humans looking at stuff, can we just have a machine that makes a decision about it? And it was decided that a machine can't decide that you're Concordia, the university in Montreal, but a machine could maybe decide that you control concordia.ca. So the idea of a DV certificate is it would be automatically issued, no humans involved, and so it's cheaper, it's faster to get it, and it's not checking identities, it's only checking, do we think that this public key belongs to the person who controls this domain? Okay, so we're going to bind together the domain name and the key itself. All right. It's vulnerable to name squatting. So, for example, let's say I go to Google with 3 O's. I can get a certificate. If that's my domain, I can get a certificate for it because I control it. I couldn't get an EV certificate that says I'm Google, the company in Mountain View, California, but I could get a DV certificate for this. Okay, so that's one of the problems with it. But other than that, it's no different as far as anyone's concerned. If you go to a website, you don't really know. Okay. Now, we just went to Concordia's website. I showed you the certificate. What was it? Was it an EV, an OV, or a DV certificate?
Probably EV.
So probably EV. Was DV when someone checked? Okay, does anyone know or remember?
No.
Okay, that's the main point, right? You went to the website. I showed you the certificate. It was there somewhere, but like no one knows, right? And so that's the way most of the web works. We just don't really pay attention to this stuff. It's kind of there.
So why pay the extra money to have the EV?
So that's a good question. So there's no good answer to
There's
that.
no real reason.
Yeah.
So
yeah.
what's the difference again between
Yeah, so
EV and DV?
between, sorry?
EV and DV certificate.
So EV will put in the company name and DV will not.
What do you mean, like, by the company name?
Like it will say Concordia Uni.
Concordia is in the two. Like, for example, concordia.ca.
Yeah, but Concordia.ca is not the like anyone can register Concordia.ca, right?
Okay.
If you got to that in 1980 before Concordia had a website, if you were like, I'm going to go register Concordia.ca, that would be you. Yeah. But this isn't you.
So the only difference is the name?
Yeah, the main difference is just that, yeah, it tries to say more than just the domain and the key. It tries to say who owns it.
And the OV?
So the OV and EV is just whether this is a registered business name, a government registered name, or just an asserted name.
So OV and DV are the same?
They're basically the same, but they're
So
slightly
is it
different.
mainly for the organization and businesses?
Yeah, both of them are for it. Yeah, EV just has some extra steps, and they check with the government as well.
Okay.
Yeah, yeah.
In the request, the CSR, right? You put the name of the whatever that you want to claim. I mean, the country, the address, stuff like that. But
Yeah.
I think that is the DV that you're doing. I mean, it's automatic. So I mean.
Yeah, so when you put the details in the certificate is filled out by the person requesting the certificate.
Yeah.
Yeah, but then when you pay for the certificate, they'll say, okay, what do you want the EV, OV, or DV? And if you're like, I want a DV, but I put Concordia University, then they'll say, okay, well, you got to drop those fields. Like, we're not going to sign off on it because we're not checking that information.
Got it.
Yeah, yeah. Okay, so Concordia happens to use an OV. Not that you would know that, but that's what it happened to use. How would you know it? So the first thing is this is kind of small, but it slightly changes a bit. So DV, Google themselves use a DV. So it basically just says we're google.com. And I circled the wrong thing. Actually, I should circle this up here. But it just says that it's google.com. That's it. We don't know it's Google in Mountain View, California, or anything like that. OV says it's in Canada, Quebec, Montreal. It's Concordia University. And then an EV certificate would be like PayPal. And so PayPal, you can see that there's a business number there. So it says private organization. It's registered in Delaware. It has serial number 3014267. So there's some more information there. And then you can also see that Apple includes a little bit before you click on more detail. There's an extra dialogue there. And it says DigiCert has been identified as has identified PayPal.com as being owned by PayPal Inc. Okay, so that's what the EV certificate gets you now. Instead of green, the person has to click on certificate
Professor,
details.
you said, the main difference is that they show the organization name. Like I see the organization name in the three of them.
So the organization name is not, I circled the wrong thing. That's my mistake. Google is, this is Google Tech Services. So sorry, Google is their own root certificate. So I circled the certificate that issued it. This is the identity of the person who issued the certificate. So forget about this. What I should circle is this itself. In fact, now that I say it, I'm just going to fix it now. So a certificate's going to include information about who the certificate's for, and then it will also include information about the company that issued the certificate. So here for Concordia, it's cut off, but you can see Global Sign is mentioned here because they're the ones that signed the certificate. So that's why Google's name is showing up on the certificate. It's
So it shows who signed them, right?
so what shows what?
Like here, global sign.
Correct. Yeah. Yeah. So the certificate will show who signs it.
And here in the DV, Google signed for themselves by their
Yeah, so
Google
Google-
certificate.
Google is they're big enough to have. So I should have a better example where they're not a CA, like it's a DV certificate for some website that isn't a CA, but yeah.
They issue their own root certificates.
Yeah, so they have a root certificate. Yeah.
So what's the extra things between OV and EV? Like in
So see on the top line, there's an extra thing there. Let me, I'll show it to you live. Maybe it will go a little better. So Concordia is OV, yeah? So I don't know anything at this point other than, it doesn't say not secure, so I know I have HTTPS. Then I have to click on connection security details. And here it doesn't say anything. It just says I have a connection to concordia.ca. Doesn't say the name of the organization. Then when I click on show certificate, then I'll see some information about Concordia here. So this is an OV certificate.
Okay.
Okay. If I go
Say
to,
it at the top too.
let me pull it back up.
I don't know if it always does in every case, but we're issued by Global Sign RSA OV.
Yeah, that
as
too,
well.
yeah.
So it does actually say the words OV somewhere in this instance.
Yes, correct. Yeah, so a lot of the name of the intermediary, like Global Sign will have CA for EVs and OVs. So they themselves will, that's how they keep track of who they sign for. Yeah. So that just happens to be in the name of the intermediary, but that also is a tip-off as well. Yeah. So a DV certificate, let's go to my website because will be DV and it will not, I'm not a CA, believe it or not. So here you can see, like, it just says pulpspy.com, that's it. Yeah. And then the person who issued my certificate is called Let's Encrypt. And then if we go to PayPal, so you see this extra sentence here. This is new, right? So it says DigiCert has identified PayPal as being owned by PayPal Inc. in San Jose, California, US. So that's a new sentence that wasn't in any of the other certificates. That's what an EV certificate gets you, basically, is that extra sentence. And then if I click on it, I also get to yeah, I can put in my business number and a few things like that.
So it's not any more secure, it's just so that you could like sort of know that it's a registered business.
Okay, so what's the threat model here? So it is more secure for an EV. It's harder to impersonate. As an attacker, it'd be easy for me to get a DV than an EV for someone I was attacking for. But users would have to know to expect an EV. Because let's say say I attacked PayPal, and the best I could do was get a DV.
They won't know.
Yeah, I'll just drop a DV in the middle, and the user's probably not going to say, oh, that's weird, I was expecting an EV certificate. If they were, then there would be a security difference here. But if they're not clicking on things and looking, then they're not going to know the difference, and they'll just say, okay, that's fine, right? And so that's the big overall lesson, yeah,
So what's
of
the
this.
solution in this case?
So just you got to make DV secure. Basically, yeah, because everyone either uses DV, or if an adversary uses a DV, you're not going to know the difference, anyways. Yeah. Yeah.
I was going to ask, if you opt for EV or OV, does it prevent like an attacker from like will I say name squatting your domain,
So-
your website?
So it won't stop the name squatting of the domain name, but it would stop the name squatting of the company name. Yeah. So like only, and that's because the government would stop it. So if someone tried to register PayPal with 2 A's,
Yeah.
then the government won't say, they'll say you can't do that, or
Website can be like PayPal with 2 Y's.
exactly, or PayPal will sue that company and do a lawsuit, and then it will get resolved. Yeah. Okay. And then if you want to know, so here we sort of inferred what it looks like that's different, but it's still not telling us explicitly that it's EVOV. So there you have to go digging into this like policy ID field, and then there's like some weird number, and this weird number will look different. If it's an EV, it will look like this. Sorry, on that far side. If it's DV, it will look like this.
So some, oh, go ahead.
Yeah.
Is there a reason that that message was so subtle that no additional message at the pop-up? It was just, it could be better, maybe there's a reason.
So this was the original idea there, and because this failed, that's why it's so subtle. So like it wasn't intended to be subtle. It was intended to be in your face, but people just didn't understand it, and so now they say, well, what's the point? We'll make it subtle.
So in the case of Google, since it's just a DB, you could, if it was available, which I'm sure it is, Google would like 3 O's would be allowed.
Yeah. So there's nothing. That's a different DV certificate. It's a DV certificate for a site, and if you own it,
Yeah,
then you can.
Doesn't matter.
Doesn't matter. Yeah. Okay. How do you get a DV certificate? So how does, let's say I go to Let's Encrypt, I'm pulpspy.com. How do I convince them that I own that domain? Okay. And I want this to be a computer system. I don't want to call someone up or send emails or things like that. Well, we're going to do an email loop anyways, but it's going to be fully automated. So what they want to do is they want to establish whether I own that domain or not. So I'll show you the process they use. They use one of 3 things, but they're all kind of very similar. What I'll do is I'll go to the certificate authority and I'll say, I own domain.ca. And they'll say, okay, that's fine. I want to prove that. So what I'm going to do is I'm going to send an email, like an automated email. I'm going to send it to admin@domain.ca. And inside that email, there's going to be a code, a one-time password, a secret link, something like that. You're going to take that code, you're going to copy paste it back into my website. And if you can tell me the code that I emailed to you, then I'll believe that you control that domain because you were able to get that code out for that email. Then I'll sign off on your certificate and everything's good. Okay? Make sense? Okay, can you think of any, if you're an attacker, we're doing an attack tree. Remember, we're attacking the arm in the parking garage. Now you're going to attack this system. What are you going to try to do?
You could give intercept the code somehow, unencrypted.
Okay, so we could try to intercept it. Let's go with that first. Emails, are they encrypted?
Yes.
Yes, no?
Yes.
It depends. Okay, a lot of people said yes. Like, could you imagine emails not encrypted? I mean, it's 2026. We have encryption everywhere. But guess what? Email is not encrypted. Okay, so email, at least it's not properly encrypted, I'll say. So there is some level of encryption. It's called like link to link. It's also trust on first use. So if I send an email and I've never sent an email to that account before, I don't know the key of that server. So what I do is I just ask it. I say, I've never talked to you before, give me your key. If an adversary is on the wire, they replace it with their own key. Now I have the wrong key and then they can read all my email. Okay, so that's the email has no, it has no secure tunnel between you, the sender, and the recipient, or even between your outbox and the recipient's inbox. So there's none of that. Yeah. So if you can access email, if you're in the middle, you'll just pull the email out. Yeah.
I think Gmail added something recently, like a padlock. I don't know if it's
Yeah. So in Gmail, what will happen is I'll have an encrypted tunnel from me to Gmail. But then I write my email, I press compose, and then I press send. Now Gmail has to send it to Concordia. That's where there's no encryption. If Gmail sends it to, if I send it to another Gmail user, it will never leave Google. Then there'll be encryption or at least security there. It's not going over the open internet. But as soon as I go to some other thing, some other domain,
It's out of their hands.
yeah, then there's no reliable end-to-end encryption between those 2 points. Yeah. Okay, so email's great. Anything else we could do?
I saw your paper on this model. I saw your paper based on the Gmail.
Yeah. So there is, yeah, I wrote a paper about all the different email attacks and things like that. Yeah. So aside from email itself, how does the email find its way to where it's supposed to go? Like I type in pulsefy@gmail.com and I press enter. How does that email get to Google? Okay, but how does it know where? So IP address, where is it getting the IP address from? From DNS, yeah? Our friend DNS, yeah? Okay, so DNS is in the loop. So what I'll do is I'll go to DNS, but I'll say, don't give me the web server, which is called the A record. Give me the mail server, which is called the MX record. So your DNS record will have a couple different IP addresses. You might have the same IP address, the same physical server might do email but you could have a different machine technically for email and a different one for your web server. So you'll get a bunch of IP addresses from DNS, yeah? Is it secure? Is my DNS lookup secure? No. So if an adversary is in the middle, could they route that email to their own IP address? They can. Okay. Now you have to be between the CA and the CA's DNS. So that's not like quite in the middle between the user. But anyways, if you were there, if you could poison DNS or do anything like that, how does that DNS record get updated? So somebody was able to put that IP address of that mail server into DNS. How was that done? Well, username, password, right? I registered with GoDaddy, so I have a username, password with GoDaddy. If someone can guess my password, right, then they can go. If you can guess my email password, admin@domain.ca, right? What protects that? Why can't anyone just log into that directly? Okay, it's just an email address. All right. So there's a lot of attack surface here. You could have physical access to the server itself. So if I can get into the mail server, either physically I'm in the server room or I get remote access, then I can pull that email off. If I can pull that email off, then I can get a certificate for the website. If I can guess or steal the password for admin@domain.ca, then I can get the email. If I intercept the email, then it's fine. So there is some encryption, but it's not proper end-to-end encryption. We call it opportunistic, link-to-link, trust on first use. This is just a reference to the paper that was mentioned. You could try to guess the value as well. So you could just blindly guess it. But normally the code would be long enough and random enough that it would be hard to guess. Another attack is, well, who owns admin@domain.ca? What's the assumption here? The assumption is that only the person who owns that domain owns that, right? What if you went to Gmail and they said, what Gmail account do you want? And you said, I'll take admin@gmail.com. Would they give that to you? Why not? Okay, well, first off, it would be taken for sure. But yeah, they somehow have to know that this is a special email address, right? So that's like common knowledge. It's not written down somewhere. Okay. Is this the only special email address?
No.
So what are some other ones? So there are a bunch. There's like hostmaster, postmaster. So there's a bunch of things that people are just supposed to know that they are supposed to reserve. Okay. What does admin even mean? What does the word admin mean?
Administrator.
Okay, short for administrator. What language is that in? Okay. Does everyone in the world speak English?
No.
Does everyone who has a browser and has a CA and has a website, do they all speak English? No. Okay, so could that be the word for administrator in any other language?
French.
It could, right? The CA in that country might allow you to do that. All right. So you would have to know. So if you're a domain and you own a domain and you're handing out email addresses, you need the list of the email addresses that you're not supposed to hand out. Okay?
In every country.
In all languages, all countries, all that. So how many are there of those? So no one knows. And it only takes one CA to use something that nobody knows. Like there's one CA that they just offer, like we'll send the email to, you can pick from these set of special email addresses. And they have some weird one like SSL certificates at domain.ca. But like the common web just doesn't know that that's a special email that's supposed to be reserved. Okay? So this is what happens sometimes. So there's an example where it was literally SSL certificates. They went to live.com, which is Microsoft's email thing where you can, it's webmail. And so the person said, I'll take SSL certificates. And then they found a CA that would send this kind of email to that email address. And then they were able to get a certificate for live.com. Live.com isn't just email, it's like a lot of Microsoft infrastructure, right? And so they now have like a certificate for all of Microsoft. Now, they were luckily a security researcher, so they made it expired. They asked for an expired certificate just so to prove that they could do it, but it wouldn't actually be used. There was no vulnerability there, and then they reported it. And but yeah. So how many of these are there? Here's a list of a bunch, and this list has. You can see there's a whole bunch there. And then some people are like, that list isn't complete. You need to add this, you need to add this, you need to add this. And so now you can get like a list, you can buy this list, and it has 1,250 addresses that you should never hand out.
Why is it needed? I mean, this amount of special words.
So it's just convention. So it's not needed, absolutely not needed, but it's just CA started offering these things and that's it. Yeah, it's crazy. Like it's completely out of control, right? But there's nobody to put control back into the system. Okay, then you can try and attack at the DNS level. So you could try to get that DNS record pointed at you. Then you're going to get the email. So it could be a DNS attack. It could be guessing the password for the registrar. In social engineering, I'll show you an attack where it was based on getting email that was redirected from DNS. Okay, then there's two other variants that are very, very similar. For HTTP or API, it's the same idea, but what you're going to do is you're going to just host your request on a domain. So you're a file in a special location. So you'll say, I have a copy of my public key. It's sitting on this file. I'll go to the CA and I'll say, I'll prove to you that it's me. Just go to this domain at this file and you'll see that this is sitting here. It's basically vulnerable to all of the same stuff. Like if you can corrupt DNS, if you can intercept it in the middle, if you can corrupt the web server, it basically has more or less the same threat model. The CA has to grab it over HTTP. Why? Because if we grabbed it over HTTPS, that would imply you already have a certificate. So the CA can't grab it over HTTPS unless if you already have a certificate. If you already have a certificate, then unless if you're renewing a certificate, you're probably not in the market to be buying a certificate, okay? So it's gonna have to go over HTTP because a bunch of people who've never had a certificate are gonna want to buy one for the first time. And if it goes over HTTP, anyone in the middle can change. They can just hijack it or they can rewrite their own key in for it. And then, sorry?
How would they now know like somebody has?
They wouldn't. Yeah. So until you see it in the wild or something like that. Yeah, so similar threats as well. And then there's another idea of if we're going to DNS anyways, like we're getting this MX record to send the email, why don't we just put the key in the DNS record? If we just put the key there, then when I fetch it, I have the key. I don't need certificates. I don't need anything else. Okay? So again, the threats are actually better. Like there's no email in the loop. There's no HTTP in the loop. It's just about you and your DNS connection. But it puts a lot of emphasis on DNS. So if DNS is wrong, or if an adversary is in the middle with DNS, then you're going to get the wrong key. So if you had DNSSEC, where every DNS record is signed, then we could start exploring whether this world would work. And it could actually be a good solution. Some people think it is a good solution, but without DNSSEC, it's not a good solution right now. Yeah.
They're signing the keys somehow, like the wrong key won't work.
so the
Man in the middle in HTTP and
so in DNS, what they'll do is they'll just replace. So remember, I'm asking what the public. Yeah. Okay. So the CAs. So you go to the CA and say, "Here's my public key. Sign it." And what the adversary is doing is they're replacing what you're saying your public key is with your own public key. So the adversary is putting their own, and then the CA will sign it, give it back to the adversary. Now the adversary has a certificate. Yeah. Okay. Now, okay, so how does the certificate authority know the key of the website before signing it? They use one of these methods. They send an email, they do an API fetch, they check DNS. Why can't Alice use the same method? Okay, well, she can't send an email to admin. Like imagine you're going to google.com and you're like, I want to know what your certificate is. So I'll just send an email to admin@google.com. And if you click on the link and tell me your certificate, then I'll believe it. That's not going to work, right? Like it's too slow for doing it. But in theory, you could. Theoretically, hypothetically, you could do that kind of thing. It's not really scalable or practical, okay? So it's more efficient for the CA to do it once, give them a certificate. Now they can show that certificate to 10,000 users a second for the next 2 years. And then they go back and they do this process once. But if you're putting it into DNS, the user is going to DNS anyways, right? So if everyone just put their public keys into DNS, I have to go to DNS to get the IP address anyways, right? So why not just grab a copy of the key there? Then I literally can do what the CA is going to do anyways. I'm already doing it. And this actually makes a lot of sense, okay? We could completely get rid of certificate authorities if we just put public keys into DNS, okay? The only difference, so the only sort of problem with it is if there's a man in the middle between me and DNS, then I can't trust anything DNS says, including any keys that I get from it. If we had DNSSEC, then this would work. So there's a proposal called Dane, which is basically put your public keys into DNS and use DNSSEC. And if you rolled out Dane tomorrow with DNSSEC, we could just get rid of CAs completely. And basically, everything would be like a DV. Maybe you wouldn't get rid of them completely. You might still have them for EV certificates, but for DV certificates, you could just get rid of them. Yeah.
What's Dane again?
Dane just stands for, I forget, like DNS authenticated named entities or something like that. But it's basically just this proposal. It's the name of this proposal itself.
So how could it like eliminate the CAs?
Because you get the key directly from DNS, so you don't
need the CA.
You don't need the CA. And it doesn't technically get rid of CAs because DNSSEC has CAs. So DNSSEC, DNS people are signing things, but there's a whole CA model in DNSSEC itself. It's a lot more sane because the TLS model was made 30, 40 years ago and we were stuck with it. DNSSEC is only 10 years old, so there's only 2 root certificates in DNSSEC. So like the IETF, the internet sort of people, they own one, and VeriSign, the biggest CA, they have the other root. And so that's it. There's just 2 root certificates. So yeah, it's a lot more sane. But there's a lot of other problems with DNSSEC, and efficiency is one, because every record you get is now like 200 times bigger because there's all these signatures and stuff, crypto stuff, and maybe a chain of certificates back. So anyways, we don't have DNSSEC, so this is a no-go for now, but in the future maybe we will. Okay, the other thing I would say is that we talk about certificates as being authorities. Authorities implies that they have authority or they have special knowledge. A certificate authority doesn't know anything. Like you might say, oh, VeriSign, somehow they know what Concordia's public key is because, I don't know, they know the people at Concordia or something. They have some special insider knowledge. They don't, okay? They literally just send an email to admin@concordia.ca, and if the person can reply back, then they say, you must be concordia.ca, okay? So they aren't really authorities. They're not authoritative over what key belongs to what organization. They just have like a bag of tricks that they use in order to do it. They've been doing it for a long time, so they're good at it. But other than that, they don't have any special insider information. So they're not really authorities themselves. And they're trusting that DNS is working and email's working and HTTP and all these protocols are working. People's passwords are staying secure and things like that. So there's a lot of trust. The other thing that's sort of interesting is that in HTTPS, we're using true cryptography. We now have keys, none of this like username password stuff. We have keys and certificates and things like that. But if you can get the right the right password, like to someone's DNS registrar or to their email server, then you can defeat all this cryptography. Okay, so the whole system still boils down to just passwords staying secure, even though there's all these keys and protocols working correctly as well. Okay, so it's not as like sort of sophisticated as you would think. So if we put this in our attack tree, we could try to get a valid certificate. We could break the tunnel. That's the sort of missing piece. But what we could do is we could try to break the tunnel by getting the tunnel pointed at us. To do that, I just need to get a valid certificate, or that's sufficient. There's going to be other things that I can do later in the attack tree, but one thing I can do is actually get a proper Google certificate, even though I'm not Google. Okay, how am I going to do that? Well, I could hack a CA, so it's happened before. I could try and break the issuance process. So if it's a DV certificate, I could try any of those attacks on the email-based verification. If it's DNS or HTTP, it's similar. I didn't fill in the whole tree for those two. And if it's an EV certificate, I could use social engineering. If the CA is in a country where I have legal pressure, I can put legal pressure on the CA. I could try and do that. And if I'm an organization and I install root certificates, custom root certificates on your computer.
Like you mean the government can put pressure on the CA and...
Yeah, just say, give me your key.
And they do it?
Well, they could, in theory. So...
you gave an example previously, right?
Yes, yeah. So in that case, we don't have any evidence that they did it for SSL, but they did put pressure on the company to put spyware into phones. And they were caught doing that, and then the spyware was taken out of the phones. So if the government can do that, then in theory they could do this, but there's no evidence that they have done that. It's a hypothetical attack. But.
Linux command to generate a certificate.
Yep.
But what does that do?
It generates the unsigned certificate.
An unsigned.
Yeah, or a self-signed.
So
Self-signed just means you sign it yourself. You're your own CA.
When you have that,
It doesn't chain back to anything, so no one will accept
so,
it.
But so you can't use that over HTTPS?
You can use it, and the user will see an error.
Oh.
Okay? And then the error might say something like, oh, this looks wrong. Do you want to proceed anyways?
Okay.
And then what are users going to do? Okay, so we'll get there, right? But anyways, yeah. But you will see an error for sure. Yeah. Anyways, if someone has access to your root store, they can install a root certificate. Or if one of the companies that makes one of these interceptions is able to convince a CA to give them a certificate, then they can intercept it. But that will get you kicked out if it gets discovered. Or if you install some sort of parental software, antivirus, that kind of stuff. Sometimes that software will also man in the middle your connection so that it can also inspect encrypted traffic itself. And the way it does that is by putting a custom root certificate in it. Okay? So your tunnel ends before it even leaves your computer. You have a tunnel between you and the antivirus software. Then the antivirus software is supposed to make a tunnel between it and the server that you're going to, but you have no insight into what's happening there. So it might be making an old tunnel, like using old crypto or something. You have no idea really what's going on. So my colleague, Mohammed Manan, has a bunch of papers on what happens with these antivirus softwares and do they make good tunnels. And they find all sorts of problems with how they do stuff. Okay, questions about this part of the attack tree? Okay, so it's a good place to break. So as I mentioned, the rest of next lecture, actually there's quite a bit of content. So I sort of sold it as being like less than a lecture. It might be, I don't know how long it will take to go through it, but what I'll do is because it's Friday before the reading week, I'll just post it online. So it's on Moodle, you'll see that there's a video, and it will have the next lecture. So you can skip next Friday, and then I'll see you all in
it's not
3
on-
weeks from
it's
today.
not on the Zoom, right?
Not on Zoom, not an online live lecture, a pre-recorded lecture that's on YouTube. You can watch it before you come to the next class. But the next class, we're going to change topics anyway. So even if you wait all the way until the final to watch that video, it doesn't matter, because the next topic will be on something completely different.
Thank you.
Clear? Yeah, okay.